Section 7.4 is on page 3 of 4, talks about basic theory of systems of first order linear equation. So, if I glance at this, and I think of this as, this is the derivative vector, this is a matrix multiplied by x1, x2, x3, so this is really a x, and this is a function g of t, g1 through g sub n, right? So this is an m by n matrix. I can write this and the x's are really those x's. Now, if I write x prime equals, they call this p of t, a capital P for a matrix, multiplied by x, and x, of course, is x1, x2, all the way through x sub n, plus g of t, and it's right there. If g of t happen to be 0, this is a homogeneous. So this is just an introduction how they do things using linear algebra. They say and x1, x2 all the way to x to the k, these are not derivatives, would be the solution to this system of equations, and the goal of course is to find those. In 7.4 they give us everything that we need, they're just verifying, and in 7.5, 7.6 you really solve those. Principle of superposition, just like we did back in chapter 3, it says if a vector function x1 and x2 are solution to a system 3 being this right here, then the linear combination of c1 times x to the 1, c2 plus c2x to the 2 is also a solution, kind of like any multiple combination of those would be a solution as well. So they're repeating what we did, but they're using theorems in linear algebra. So they say here, if the vector functions x1 to x sub n are linear independent solutions of system 3 for each point in some interval, then each solution x equal x of t of system 3 can be expressed as a linear combination of those. Okay, and that could be done exactly in one way. Abel's theorem says if x to the 1 all the way to x to the n are solutions of 3 on an interval, then in this interval the wronskian either equal to 0 or else never vanish. So it's always there, meaning there's a solution. Now, let e to the 1 be 1 and a list of zeros, e to the 2 be 1 in the second entry, all the way e sub n be a bunch of zeros and 1 at the end. They say further, let x1 and xn be a solution of system 3 that I wrote up there, then x to the 1 equal e to the 1, x to the 2 equal e to the 2, and x to the n equal e to the n. Respectively, where t0 is any point in this interval, then x1 through x sub n form a fundamental set of this equation. Remember what a fundamental set is. Each of those must be a solution, and the linear combination is a solution, and they must be linearly independent. So, back to equation that I wrote up there. Consider system 3. If this matrix P is a real valued continuous function, if x equal u of t plus I times v of t, those are vectors, is a complex valued solution of this equation, then its real part u of t and v of t is the complex part, the part associated with I, are also solutions of this system, and they define the wronskian given x1, x2 be two vector functions, we define the wronskian to be the determinant of, and remember that x sub 1 is really x sub 1, x sub 2, and y sub 1, y sub, oh come on, and x sub 2 in this case would be y sub 1, y sub 2. So those would be the transpose of these vectors. And we start with an example, and again they're pretty much giving you everything that you need. You could start from scratch, and this section is just an introduction, which is a nice thing to do. They say equation 2. This is the equation, so this is like saying x prime equals ax. First you need to identify what a is, what x prime is, and what x is. They say suppose those are solutions, show that the given functions are solution of the given system of differential equation. Well, how do you do that? You take the derivative of each. So if I take the first, let's start with this vector. If I take x, again this is not a derivative, which is e to the negative 3t, negative 4e to the negative 3t. So when they say show that these are solutions, they're saying take a derivative and take this matrix, multiply it by this x, and they should be the same. And let's see if that works. So if I take a derivative of this, the derivative of this is really negative 3e to the negative 3t and 12e to the negative 3t. There, that works. Now, if I take ax, that would be 114 negative 2 multiplied by x, which is e to the negative 3t negative 4e to the negative 3t. And that would be, this is 2 by 2, this is 2 by 1, the outcome is a 2 by 1. And the way it works, you would multiply this row by this column. That would be e to the negative 3t minus 4e to the negative 3t. And when you take this for the second entry, multiplied by this vector, that would be 4e to the negative 3t and 4e to the negative 3t plus 8e to the negative 3t. And if I combine those, I'll get one of those minus 4 of those is negative 3e to the negative 3t, and 4 of those plus 8 of those is 12e to the negative 3t, and you notice that's the same. So those two are equal. This is verified. And let's verify the second piece. If I take x sub 2 prime, x sub 2, x to the 2 is actually e to the 2t, e to the 2t. So if I take a derivative of that, that will be 2e to the 2t, 2e to the 2t. Okay, now let's see if ax matches. A happened to be 114 negative 2 multiplied by e to the 2t, e to the 2t. Again, to generate the top row, I would use those two. That will be e to the 2t plus e to the 2t. And to generate the bottom row, I use the bottom row times this, again, this way, this way. That would yield 4e to the 2t minus 2e to the 2t. And if you add those, that will be 2e to the 2t, and that will be 2e to the 2t, which is pretty much what we got. So that's satisfied. First, I did show it's a solution. Second step, it says show that that would be a solution. Any linear combination of those would be a solution as well. So to do that, I would really have to say x is actually c1 times x1, so that is c1 e to the negative 3t negative 4c1 e to the negative 3t, and I'm getting this from right there, plus c2 times, and the second was e to the 2t e to the 2t, and if I add those two, I will get c1 e to the negative 3t plus c2 e to the 2t negative 4c1 e to the negative 3t and plus c2 e to the 2t. There you go. That's what this is. They say, show that this is also a solution. What does that mean? That means if I take a derivative of this, and if I take the matrix A multiplied by this, I should get the same thing. Well, let's see if that works. If I take the derivative of this, wouldn't this be negative 3c1 e to the negative 3t plus 2c2 e to the 2t? And this would be a 12c sub 1 e to the negative 3t plus 2c2 e to the 2t. And if I take ax, that would be, and what did we use? It was, what was it? 1, 1, 4, negative 2. 1, 1, 4, negative 2, multiplied by this matrix, c1 e to the negative 3t, plus c sub 2 e to the 2t, negative 4c1 e to the negative 3t, plus c sub 2 e to the 3t, and let's see how this works. Again, this is 2 by 2, this is 2 by 1, so the outcome is a 2 by 1. And to generate the first, I would use the 1, 1 multiplied by this matrix, and that would be a bit longer than this. That would be 1 times, that is c1 e to the negative 3t plus c2 e to the 2t, plus 1 times this in 3, minus 4c1 e to the negative 3t, plus c2 e to the 3t. To generate the second entry, I'm going to use those multiplied by those again. If you take 4 times the top, that's 4c1 e to the negative 3t, plus 4c sub 2 e to the 2t. And a negative 2 times this, that will be 8 e to the negative 3t, minus 2c sub 2 e to the 3t. I lost a c1 there. Let me recap. That is 8c1 e to the negative 3t. And if I combine those, if I add those, c1 e to the negative 3t minus 4 of those will be negative 3c1 e to the negative 3t. And if I add those two, I'll get twice e to the, that should be 2t, right? And if I take those two and add them, wouldn't that be 12c sub 1 e to the negative 3t? And if I add those two, I should write bigger, huh? That would be 4 minus 2 is 2c sub 2 e to the 2t, which is pretty much what I got there. So it does show that a linear combination is also a solution. Now, show that the given function form a fundamental set. How do you show that it forms a fundamental set? Fundamental set, the first should be a solution, the second should be a solution, and any linear combination is a solution, and they must be linearly independent. So how would you show that they are linearly independent? First, so to form a fundamental set, you would show that 1, x to the 1, x2 are solutions, and we just did that in part A. And 2, how do you show that they are linearly independent? You would say if c1 times x to the 1 plus c2 times x, I'm mixing that, there we go, equals 0 vector, if and only if c sub 1 equals c2 equals 0, that will show that they are linearly independent. So if I take c1 times x1 that would be a negative 4 c sub 1 e to the negative 3t plus c sub 2 times e to the 2t, c sub 2 e to the 2t, and I say that will equal c sub 1 e to the negative 3t plus c sub 2 e to the 2t, negative 4 c sub 1 e to the negative 3t plus c sub 2 e to the 2t. So basically, this is right there, and this is right there. And if I set that equal to 0, 0, I need to show that c1 equals 0 and c2 equals 0. And if I do that, let's see, we're looking at a system of equations, right? We're looking at c1 e to the negative 3t, c2 e to the 2t, negative 4c1 e to the negative 3t, c2 e to the 2t. I'm using augmented matrix form. If I take 4 times row 1, add it to row 2, put the result in row 2, what would happen? I would be looking at, multiply this by 4, that will be 4c1 e to the negative 3t, plus that's a 0. And if I multiply this by 4, that becomes 4c2 e to the 2t plus 1, that is 5c2 e to the 2t. There are 7 ways you could show this. Well, this means 5c sub 2 e to the 2t equals 0, right? Well, we know that e to the 2t can never equal 0. It must be that 5c sub 2 equals 0, which indicates c sub 2 is 0. And if I go to the first equation, backward substitution, c1 e to the negative 3t plus 0 equals 0. Again, e to the negative 3t can never equal 0. It must be that c1 equals 0. And there it is. Since those are 0, we have just shown that those are linearly independent, and that forms a fundamental set. And what if they told us there is the another way you could do that, I'm sorry, I forgot to mention, you could have used wronskian. You could have used the wronskian and show it doesn't equal 0, just like we did back in the days. That works as well. And here they say, find the solution of the given system satisfying the initial condition. Meaning what? Meaning, if I take x of t, which is c1 e to the negative 3t, c2 e to the 2t, negative 4 c1 e to the negative 3t plus c2 e to the 2t. Again, the first vector and the second vector, right? And if I take x sub 0, so replace t by 0, wouldn't that be c1 plus c2? And wouldn't that be negative 4c1 plus c2? And I want this to equal the transpose of this. So 1, 2 transpose is actually 1, 2. And I want to solve this equation. So if I really write this in augmented matrix form, it looks like a C1, actually, it looks like a 1, 1, negative 4, 1, and a 1, 2. So to solve, I will take 4 row 1 plus row 2, put the result in row 2. So 1, 1, 1. Multiply this by 4. 4 plus 4 is 0. 4 plus 1 is 5. And 4 plus 2 is 6. So this tells me that C sub 2, 5C sub 2 equals 6, C sub 2 equals 6 fifths. And C sub 1 plus C sub 2, but C sub 2 is 6 fifths, equal to 1. C sub 1 equal 1 minus 6 fifths, which is a negative 1 fifth. So I would say x of t equals negative 1 fifth x1 plus 6 fifth x2, which would be negative 1 fifth times 1 negative 1 e to the negative 3t plus 6 fifths 1 1 e to the 2t, and that would be a negative 1 fifth e to the negative 3t plus 6 fifths e to the 2t, and this will be 4 times 4, oh, this was a 4, wasn't it? Yeah. Negative 4 fifths e to the negative 3t plus 6 fifths e to the 2t. That would be the actual solution for this system. And the last thing they want us to find the wronskian. Well, the wronskian, go back, erase this. The wronskian, and if I list e to the negative 2t, remember I list them this way. If I list x1, x2, x1 is e to the negative 3t, negative 4 e to the negative 3t, and x2 was e to the 2t, e to the 2t, they're right there, or in the beginning. If I take the determinant of that, that would be e to the negative t minus a negative 4, so that's plus 4 e to the negative t, that would be 5 e to the negative t, and we know that can't equal 0. And there's the homework. We're going to skip part F on section 7.4.